So I will slightly review these cases of a quantum gates. All right. So so this is general stuff that we already discussed. Yeah. Now there is this density matrix, and this density matrix is of that form, and then we have the following evolution of density matrix with time that is written in such a way. So for the case, okay, so maybe, okay, I will move on. So obviously we can refer to Pauli matrices algebra in a quite straightforward way, right? So okay, so let me maybe go to more specific examples. Maybe I will first start from some view on possible physical systems, on some topologies of physical systems, and then I will move to some specific equations. So I'm sorry, it's a little bit lengthy, but I try to jump to kind of interesting pictures, so then we can. All right, so this is our position-based qubit. We have reduced the system to the problem of two coupled quantum dots. That's nanotechnologically represented in such a way that there is quantum dot A and B. There is some channel, there is a gate, and this gate is able to control the tunneling rate between left and right quantum dots. And there are obviously oscillations of probability, as there are oscillations of occupancy of left and right quantum dot. So at least there must be two energy levels of populated, so this at the same time. And so then those oscillations of occupancy are time dependent. All right, and then we have two possible interacting qubits. So we don't really concentrate on their kind of detailed structure, but it's just written in a symbolic way. All right, and it's yeah. So there is a parameter angle of. So what we can control in here is so in this Hamiltonian structure, there are two parameters, AP1 and AP2. So this is like energy localized at node 1 and at node 2. And if those quantum nodes are decoupled, then this whole term is set to 0. So and then we can, yeah, so we can keep. So you can observe how we can tune this eigenenergies landscape. And basically, if AP1 is set to AP2, then first qubit and then AP1 in another qubit is -3 and -2, then the situation is of asymmetric qubits, and then this eigenenergies with distance, and there's angle set to P4. Then this so that's such type of dependence of eigenenergies on the distance. If we change this, yeah, so here we have a Hoping constant Ts that is set to 10 for all qubits, and then we can simply changing the Hoping constant, so like changing the connectivity between quantum dots in each of this qubit, in each among those two qubits, we can tune this eigenenergies, and this is essential for since we might wish to set certain difference between energies that are of our particular interest from the point of view of quantum logic. So there is a big space of possibilities. I will not go into detail. You can observe various cases. It's interesting to see that this eigenenergies never cross in such type of system. If they would cross, it would mean that like two ground states will exchange their position. It would suggest the occurrence of topological phase transitions, and this is not the case in the situation when we have two position-based qubits interacting electrostatically. However, this is the case when we have a Josephson junction electrostatically interacting with semiconductor position-based qubits. So we have superconducting Josephson junction electrostatically interacting with position-based qubit, and in such kind of system, there is a possibility of ground state exchanges, and there is a possibility of having the quantum phase transitions. And it's interesting to know that those quantum phase transitions are let's say can be controlled also electrostatically by setting voltages to the gates of semiconductor position-based qubit. So it's an interesting topic for some experiments. All right, so so the thing is that here we have a kind of swap gate. If two qubits are set in if this AP1 is set to AP2, and again AP1 is set to AP2 here, then the electron tends to be at maximum distance. However, this is not the case if so we can. So this is like logical negation, but this logical negation can be turned into ideal coupling states. So if we change AP1 and AP2, we can set that such situation when it's favorable for the system and that both electrons stay on the same side in both qubits. So there are various possibilities of tuning of this system of interacting qubits. And now, of course, so we need to consider now this dissipation effects. So usually in systems as described here, the Coulomb force is of relatively small value, so that therefore the Coulomb interaction can be treated in a perturbative way. Okay, so maybe I will just refer you to another of my papers, which where I can introduce some noise to this system of qubits. Yeah, please give me a second. I'm just trying to. So basically, how we can model this noise presence? So we can basically consider a kicks in parameters of a qubit. So we can have a kick towards AP1. We can have a kick towards AP2, and we can have kick towards Hoping constant. So in such a case, having those kicks, we can describe this this process when the system is getting some energy from outside. Yeah. So now I'm on this paper which describes this thing. So basically, yeah. So we have a situation. So initially, so we can. So we have a standard Hamiltonian AP1, AP2, and Hoping constant on anti-diagonal, and then due to presence of external charge that happens to pass by the given qubit, what happens is that this AP1 can have added value by a function f1. It depends on time. AP2 again can have a function that that is f2, and again f3 and okay. So now here it's done under the circumstances that still the system evolution is unitarian, but in principle, there's values of f1, f2, f3, and let's say f4 can be complex value. So we can introduce kicks to the system by some Dirac delta function, and this Dirac delta function can be parameterized by noise. So this noise can happen in polarizing gates or by presence of external flow of charge that is in close proximity to the qubit under our consideration. So it's just to give you some view. So basically, if we refer now to the Schrödinger picture, this AP1 is it's dependent on this Wannier function of left quantum dot, maximum localized wave function, in such a way. So there's some potential that comes from polarizing gates, and there's also some time-dependent external potential that is not well accounted, that can result in effective change of this AP function. So in general, it can be also dependent on position. So this can happen. This can happen in such a way. So in the considerations that are just given here, I was just analyzing the case of the passage of an overcharged particle, so that therefore this dependence on position was neglected. So it was very much phenomenological description. So that's how to relate things into more microscopic picture. All right. So basically, in general circumstances, they are divided into equation 11, and in equation 11, the system is under evolution with time, and there are some presence of some. So there's assumption that at time t1, there is some appearance of external electron or charge that's affecting the state of qubit. So the system is subjected to some kicks. So this is like Brownian. And so these kicks can reproduce you a kind of Brownian-like motion, but for the quantum case, right? So there are certain jumps. And you can imagine that the situation will become much more complicated if you have quantum gates. If you have a system at least more than just one qubit, then these kicks for one qubit will affect the state of other qubits as well. So you can model the propagation of these kicks among the whole quantum system. So yeah, it will be a kind of like quantum Brownian motion. All right. So okay. So this was one side of the description of the decoherence processes. Okay, maybe just to give you more pictures. So yeah, so there was a moving charge. So initially it was gray, and after moving charge was appearing, the gray potential was renormalized to another orange potential, and this orange potential has different AP1, AP2, and Hoping constant. So this kind of explains through this phenomenology of this decoherence effects treated by Binding model. Right, so let me go to maybe some more specific structures. Okay, so basically, yeah, you can have a system of two swap gates. And so of one swap gate with two parallel qubits, and there is movement of electron by nanowire, and this will generate a kick for first qubit, and this kick will propagate further. So actually you can use this external charge to set certain quantum state of such quantum logical circuit. All right. Yeah, I will not describe details. So basically, just to let you know, we can have the whole zoo of qubits of different topologies that can be represented in the same type of formalism as it was described. So we can have two parallel lines. We can have a V-shaped parallel line. You can have all sorts of topologies, and basically you can use this type binding approach. And so this formalism is quite powerful because it's very simple. And obviously you can extend it further to more detailed picture, but at least first insight can be simply by this type binding model. All right. So okay. So this was the case. Yeah. So now I will move to more detailed picture of dissipation. If we start from the case of non-interacting qubits, so maybe I will move to another document. So this was the title that was sent to you. So it was analytic view on n-body interaction in electrostatic quantum gates and decoherence effects in periodic model. But this decoherence effect will simply mean not escape of an electron from a given origin, but just an uncontrolled evolution of a quantum state due to external Coulomb interaction. Yeah. So first of all, sorry for this algebra. So we have AP1, AP2 TS hoping, and then we can have the eigenenergies in asymmetric case. There's AP1 plus AP2 as a parameter, and AP1 minus AP2, and TS always occurs with a square. And then you can decompose the eigenenergies, like ground energy, into such term of occupancy of left quantum dot by spanning coefficient A and B quantum dot, and second quantum dot, and there is a coefficient B. So those coefficients are quite nasty in algebraic structure. It's arguing here, and again, this was for a ground state, and for excited state, you have C and B as the coefficients in front of this linear function. So again, C and D are kind of nasty, and they are of such form. Okay, and then you can describe this evolution of a quantum system under consideration. So so essentially, yeah, so I wanted to describe some kind of tricks. So just before, so okay, maybe I will just okay, maybe I need to switch back to this camera stuff, unfortunately. So I will set it again. Yeah, so I have to turn this screen sharing, and it's not that easy. So I don't know what's going on, so I'm just, yeah, I have your system showing. All right. Yeah, can you see this? Please confirm by chat or something like that. Maybe I will just describe it in very analytical ways. So what happens is that if you have a qubit A, its quantum state is its Hamiltonian configuration in such a way. So presence of energy on the left side, like localized energy on the right side, plus S1, 2. Okay, so there is this opening from 2 to 1, so this will be from 2 to 1, so will be like that, plus opening from 1 to 2. Okay, so this will be then minus 0, 1 and 1, 0. And the same can be done with qubit B. So there's, I suppose, to write it index A everywhere. Yeah, I'm sorry, it's kind of tedious, but so this is for this system that 1. Then it's like this, and again, let's say beta 0, 0, 1. And it's okay, so this is again for states A. Okay, which states A, and this is for states B. S1 B minus B 0, 1, 1, 0, right. And there is identity operator that shall be used. So this identity operator is this identity operator is simply projection of the system on itself. So it will be like down here, right? And this is both for A or B. So this is identity operator for A and for B. This is how it is. So Hamiltonian or non-interacting electron is nothing else as a system times I identity for B plus IA times HB. So that's how it is. So, and then there is this Coulomb term that has to be counted. So this Coulomb term, first I have to write down this kind of this physical situation. So 1, 2, 1 prime, 2 prime. And there are some distances. Okay, so this is the qubit A and qubit B. Yeah, and then we have to have this representation of the states. So 1, 1 prime, 1, 1 prime, and then there's transfer over this distance. So the 1, 1 prime plus again, so everything else is in a kind of repetitive way. The prime, d2, the prime plus 1 to prime, 1 to prime. So it's like this, 1 to prime and to this needs to be to 1 prime, and that's how this be to 1 prime. So we have situations here, and now, yeah, and now, so you can imagine that there will be change of. So if this is, so it's very interesting to see that what will happen is that during this evolution, there will be so we have two energy level systems. We can treat each qubit as an energy level system, and due to this interaction, so there will be integration as there will be certain occupancy of two energy levels, and for one qubit, and two energy levels for another qubit, two, and this occupancy of energy levels will continuously start to change. So for isolated qubit, this energy levels, occupancy levels are fixed, and so you can see external qubit as source of time-dependent electrostatic field. So there will be continuous changes of occupancy T1, T2 due to this qubit-qubit interaction. Maybe I will move you to some more specific description with some of my notes. So please give me a second. Okay, so I will. Yeah, so maybe I will do this screen sharing for. Yeah. So again, this. I have to share this Acrobat Reader. So now, okay. Did I show you properly? No, this was not. So, okay. Right, so that's. Sorry, it's for that. Okay, so I'm sorry for this. Let me move to more specific example. Where I want to show that some part of this calculus. All right, so this is what was already being shown, this formula 109. That's visible here. And now the trick is to see this energy transfer during this electrostatic interaction. We have to change the basis simply. So we have to move from position basis to eigenenergy basis. And then we will see that during this interaction, this qubit is exchanging one quanta of energy. So it is like mediating. So one electron is emitting some photon and it's absorbed by another electron, and so back and forth. So there's formula 109, and yeah, and this is this calculus. you remember this A, B, C, D, there was, so this is in the regime of a weak interaction. So what happens is that you have such term as for example given here, and then we use this identity operators in energy space, and we act on this operator. And there are some systematic, and again we can take identity operator here and here, and yeah, and this will lead us to such lengthy expression, but this expression will have all coefficients between various projections of energy. So energy can project on itself. So this means that given eigenenergy is not changing with time, there is no energy transfer. So here there is no energy transfer. So it's projection of energy on itself. Again, a projection of energy on itself. And now there is this game that, for example, eigenenergy of first qubit is projected on eigenenergy of first qubit, and eigenenergy of second qubit is projected on another eigenenergy. So there is a change of energy of qubit 2, or like B, of qubit B. So you can observe this transfer of energies by these projection operators. And that's a very convenient way of describing what happens with the system. So of course, it's very much visible from here that lifetime of quantum state of a qubit is a finite, because there is a possibility of projection on another eigenenergy state. So in a sense, you can say that the effect of presence of another qubit is nothing else as a kind of like Rabi oscillations, something like Rabi oscillations, under which you can change this, under Rabi oscillations, you can change this occupancy of between eigenmodes. So this can give you a clue how to predict finite time of life of an electrostatic qubit. All right, so that's unfortunately it's very lengthy algebra, but it's still quite straightforward way of thinking. So maybe I will move. Yeah, so you can do with all terms, and then yeah, we get a lot of such type of expressions. And now let us observe what happens with eigenenergies. So let us suppose that this Coulomb interactions of very small value. So initially the qubits A had eigenenergy A1A, and qubit A1B had qubit B has an eigenenergy A1B, and then this eigenenergy will be changed due to this presence of perturbative electrostatic interaction, and this will be accounted by such terms as given here. So this is effectively Q over this, by default very small value, and then you see that this, so this, like when you move from isolated to qubits that are very far distance, if you bring them closer, then there is appearance of modifications of a sum of two eigenenergies of qubits. And basically you have four combinations. So initially you have four combinations of eigenenergies for isolated qubits. So A1A, A1B, A1A, A1, A2B, A2A, A1B, and A2A, A2B. And this combination is going to be modified by the presence of this electrostatic interaction. And then it's all expressed by A, B, C, D coefficients. So A and B were the coefficients that were expressing this linear. They were spanned by two linear functions of left and right side for a qubit A, for a qubit for a ground state, and C and D were the same coefficients, but for excited state. And those coefficients, so that can evolve with time since the system evolves with time. So anyway, that's they made it for first approximation. They don't evolve with time, so they have just fixed values. So you can see how this modification is done. So yeah, so this is how this situation is described. And yeah, and there's another effect. So basically, you can have a different oscillations of occupancy, and then usually if one qubit is populating two eigenenergies, there is oscillations of occupancy between left and right that are proportional to energy difference between those two qubits. There's one cosine term, cosine, and there's a function of E excited minus E ground over H bar times T. However, if you have external qubits, then there are more cosine terms. So effectively, this evolution of a system will be different. Okay. All right. So let's say maybe I will also make a small description of the same process, but by usage of, so far I was limiting myself with use of tight binding model, and now I can do the same things with use of Schrödinger formalism. We have this, so we can always write so we have the electrostatic Coulomb interaction in such a way. This is just magnitude, electrostatic potential, and then we can represent this Coulomb interaction in such way. So in position representation, the state will project to itself, but it's not the case for representations in eigenenergies, as it was described before. And then we have this initial initial quantum state that was so for two qubits that are not yet interacting. So the tensor product of states on the left hand of first qubit and another qubit. So there's the parameterized by momentum, and that corresponds to certain eigenenergy. So there's P1 and P2. And now it's interesting to see this action of this. So basically, the system is spanned by coefficients like Q00, Q01, Q02, Q0n.